Let me ask you a question. Can you spot what's wrong with this picture? Can you spot the horrible optimization in this 2024 game graphics pipeline? By the end of this video, the problem will be glaringly obvious to you. And it all starts with the uncompressed, artist-created texture. And this one has been saved in the PNG format, where every pixel is 24 bits worth of information. A bit can only represent a 0 or 1. A byte, or 8 bits, can only represent 256 different values. 24 bits can represent over 16 million values, so in this case it's 16 million colors. If the PNG was transparent, each pixel would take up 32 bits, but let's stay simple here. If we take a look at this Half-Life Alyx scene, just so we can reference a typical texture count, around 200 textures are at least 1024 squared resolution. Now this puts into perspective how quickly those bits add up in digital storage or VRAM, but in reality it's much worse, and general content wouldn't even fit in VRAM if we used uncompressed textures for basic 7th gen games. But say we could reduce the bit size of the pixels to around 5 bits. That would reduce a massive amount of data. Games have been compressing textures for decades, and the modern approach can do better than 5 bits, using block compression. Now some programmer or some group recognized typically little variation exists within 4x4 blocks of pixels. So block compression takes into account the local variation, and as long as the texel density isn't larger than the application pixel density, you're not going to see a massive difference. There are several types of block compression which have created a division on how they should be used, but luckily, the developers of Dead Space Remake extensively studied this topic, and not a single mainstream voice has been talking about it. Now there are a lot of really important things to discuss in the presentation, but for now, all you really need to know is they created an automated texture packing system that allows them to recompile Dead Space Remake scenes with vastly different packing schemes for A/B testing. Unlike the original presentation, this shows all the data in one compact slide. This may be overwhelming at first, but it's easy to comprehend once it's explained. Base pass means all this data only relates to the cost of rendering fully textured geometry on 1080p G-buffers on Series X hardware. These are the packing schemes and their basic descriptions, and this is the hardware debug information for each packing scheme, with the final base pass cost below. Before each scheme is explained, notice the ALU stats, which measure the arithmetic complexity of material logic, show massive amounts of utilization headroom, because the draws are bound by the cost of addressing memory-heavy textures. In fact, we could double the material complexity without much impact on performance. This is particularly good news for complex tile materials where instruction counts have been known to climb up to around 1,000 per shader. But better GPU utilization doesn't mean faster performance. We need to reduce the aspect in which the draws are bound by, and this is how compression schemes affect performance. This is all simplified, but the concept of balancing ALU with memory-related assets is a core topic in this video. But these tests revealed major conclusions that go against common assumptions. The cost of BC7 compression is severely underestimated, as it performs identically to near uncompressed contents. BC1 compression, on the other hand, is insanely efficient. The shipped packing scheme of course takes advantage of BC1 efficiency, but it also lowers the resolution or completely excludes the last BC4 data depending on the asset. They use a BC5 and a BC7 because they found block compression artifacts in the BC1 only scheme, as you can see in the red. There are two issues with using these artifacts as a justification for BC5 normals and BC7 color/smoothness. Considering BC1 compression will output a higher quality if the information is relative, such as albedo or base colors, these issues are more likely coming from the BC1 normals, because normal info tends to degrade BC1's compression on a visual level. Take a look at this tangent space normal. Even a BC7 alpha with only one relative channel will provide drastically better results than BC1 compression with one relative channel. BC1 compression doesn't break like this for colored content because it's usually made up of 3 relative channels, whereas BC7 compression only needs 2 relative channels for good compression quality. BC4/5 compression is too expensive for its limited channel usage. The second issue is the fact that the microdetails are costing 0.4 milliseconds, while those details aren't going to massively enhance immersion in comparison with richer approaches. This data backs up advice given in past videos and helps identify overlooked bottlenecks in previous analysis done on the channel. If you look at the last point regarding tile material workflows, You may be confused if you think we have an issue with the 3.2 millisecond cost over the 2.8 millisecond cost. The issue with the 3.2 millisecond shipped solution isn't the cost, but what that cost offers in terms of visual quality in comparison with the TI compression scheme, which was shared about 2 months ago. Funny enough, this format was suggested for general assets because maybe you would want super high quality BC5 normals for say main character assets, but even the protagonist in Dead Space Remake uses BC7 tangent normals, further validating its viability. Now, the paper has some really incredible and unique statistics, and it set some pretty high standards for what we were expecting to find in the base pass during the analysis, but the paper data has no mention of the severe geometry issues, nor does it discuss any packing glitches that would explain the 21 extra textures included in all the base pass draws. So it's very odd reading the paper and seeing them discuss such wild success with Dead Space Remake. But nevertheless, we can validate the results here. Even in so-called debug builds, such as this, you can't detect an efficiency difference unless you use a dedicated hardware profiler, which will then display very similar results, restoring our confidence in the paper's findings. But why is this paper still so important? Because this team designed a new workflow where artists no longer had to manually pack or filter textures. All artists have to do is create a texture set with appropriately defined assets, which plugs the raw contents into the material workflows. When it's time to build the project, filtering and automated texture packing is handled by the engine. This is drastically better than what's being provided in Unreal, which is why they even ported the workflow to Unreal through heavily under-referenced open source efforts. There is a massive amount of benefits listed in the paper regarding this workflow, and while it is experimental, the multi-billion-dollar company that so-called manages the industry-standard game engine hasn't done any major public work on expanding this workflow or standardizing it. Right now, corporate efforts are focused on replacing block compression with real-time neural methods, but the potential in block compression has barely been explored by competent engineering teams. We need to build on pre-processed quality first before we go around pretending an extremely expensive alternative is the solution. But don't mistake this as an attack on AI. The only issue is the cost, and it's very possible that it could provide aesthetically superior block compression in the future. Advances in block compression and texture workflows will hopefully set an example for general assets, as this would be far more helpful for studios and artists than performance-killing marketing gimmicks. After all this compression research is over with, where does this compressed data go next? Well, if you're forward rendering like Half-Life Alyx, it's combined with uncompressed, usually fairly high-resolution shadows and cube maps, and other uncompressed forward lighting inputs so that the output is held in an uncompressed HDR format. Now, see those numbers? They're super important and fairly easy to understand when it's explained. The letters left to the numbers just represent the channel letter. The letters typically progress from red to alpha, so if you only need 2 channels, you wouldn't have access to a red-blue format. You would have to use a red-green format. Depth buffers and shadow maps use formats that typically begin with D for depth and S for stencil. The numbers just right to the letters tell us the channel bit size, and unlike PNGs that hold 24 bits of information, the total size of rendering formats are extremely strict to accommodate for hardware memory efficiency. The abbreviations or numbers right to the numbers tell us the format modifier, and while we're not going to explain each type, the 3 listed on this bullet point chart will cover the most relevant formats. The only relevant thing left for you to know is that these large format names are often abbreviated. You just take the left-hand number with the same bit sizes and put their shared number next to them, and separate the numbers based on the bit sizes, as you can see with RGB10A2. Simple forward rendering is fairly straightforward, but if we know highly compressed formats have a significant impact on performance, we become a little bit more familiar with the faults of forward rendering and how deferred rendering relies on massive uncompressed formats for later operations that could be just as texture addressing bound. Take the creation of a shadow mask for example. It's an 8-bit full resolution mask that tells the lighting stage if the pixel is in shadow or not. Only 120 bits multiplied by the internal resolution and shadow map resolution are needed for the shadow mask creation, which can reduce the amount of bits going into the lighting pass. But most game engines don't use the minimum bits for shadow masking. In most engines, the creation of these relevant formats are straightforward. But opacity is an important value that allows the shadow map to pre-compute its interaction with on-screen subsurface scattering, and since opacity is often packed with other base pass contents, many graphic pipelines like KCD2's CryEngine will send an extra 20 bits of information in the shadow mask processing draws. You could fix this waste in a number of ways, such as rendering opacity in its minimal format during the base pass, but this could create some other issues we'll eventually go over. Our Frostbite title analysis have shown that compute shader conversion is very fast, but there might be potential in a multi-purpose or Uber shader approach, as we've seen in Days Gone's custom UE4 pipeline. Speaking of Days Gone, that game uses an RG8 or 16-bit shadow mask, with the green channel containing extra information regarding skin and plant translucency, as well as a separation point between far-field shadows and the CSM shadows. The Callisto Protocol's custom pipeline does just fine with an RA or 8-bit only shadow mask. But how does Epic Games' Unreal Engine handle shadow masks? Well, let's take a look at this full-screen shadow map projection draw in Silent Hill 2 Remake. Now you can recognize the multitude of problems. It suffers from the typical inefficiency of drawing an extra 24 bits of information just to access the opacity stored in the 8-bit alpha. But the alpha channel doesn't just store subsurface opacity values. If the pixel isn't representing some type of transparent material like skin or foliage, the opacity will be assumed as fully opaque, and the 8-bit value will represent a different input for Unreal's multitude of shading models. That means if any process wants to access the actual opacity values, it has to use a second 8-bit channel that tells the shader to assume full opacity or actually reference the 8-bit opacity value. Now, because the opacity value is packed with other content, we're bloating our efficiency by around 24 bits, but if the shading model was packed inside the same render target, then we would only be wasting 16 bits. But at Epic Games, even slight optimization is a mere fantasy. So the shading model mask resides in another base pass RGB-A8, forcing another 24 bits to be wastefully processed for every single shadowed light on screen. Later on, you'll find out why this isn't even the worst issue, with a much bigger problem being that the shadow mask is a 32-bit format, which will directly bloat the lighting passes, which are already heavily texture addressing bound due to all the G-buffer and ID inputs. Preferably, it should be 8 bits, as seen with Callisto Protocol, but it's not even 16 bits like Days Gone. Later on, you'll see that reducing the bit size of formats won't always give a major performance boost, but people need to familiarize themselves with this concept because it helps understand some of the issues we've come across, like in this chart for the Callisto BRDF performance test. The lighting draws are not more expensive because the Callisto BRDF is too complicated arithmetically. The lighting draws are more expensive because of the 200 plus extra bits from the Realis inputs, which we determined are not needed, which will speed up any adoption of the BRDF. And since the deferred G-buffers will keep the lighting draws texture addressing bound, we have plenty of ALU headroom for highly configurable implicit BRDF logic. And actually, there's a good lesson to learn from the Callisto Protocol. Take for instance this lighting draw. It may not look like it at first, but if we highlight the draw and read the stats on it, we can deduce that every pixel had lighting evaluated whether it was lit or shadowed or whatnot. A simplified way of looking at this is that the GPU draw cost is a product of pixel invocations and input bit size. All the pixels on screen require the typical deferred base pass G-buffers in order for the lighting arithmetics to work, but only 4% of the screen requires the additional 240 bits of TCP skin shading buffers. A faster way to shade this light would require drawing the light twice, but with the first draw only containing the typical G-buffer inputs and stenciling out invocations for anything that's skin. Even though a similar amount of pixels are worked on, the pixel invocations will be shading everything much faster without the additional skin buffer inputs. Then the second draw, representing the same light, uses the additional skin inputs but stencils out pixel invocations for everything that isn't skin. Even though Draw 2 uses a massive amount of bits, it will only cost 4% of the original draw scheme. It would be great if Callisto Protocol shaded dual normals like this, but it doesn't. A game that does stencil out lighting pixel invocations based on resources is Days Gone. Let's go ahead and inspect this local light highlighted in pink. Days Gone uses large formats to store deferred inputs in custom-defined bits. This technique is called bit shifting, and unlike stock Unreal Engine games that use 4 sets of 32-bit G-buffer data, Days Gone's custom layout is more traditional, only using 3 sets of 32-bit G-buffer data for lighting. Days Gone's local lights don't use shadow masks either, but there may be a benefit to this, which we'll discuss later. Most of these draws just use these inputs with a stencil buffer on the side, but the skin draws access an additional subsurface scattering lookup table, but not Unreal's default version. It's a custom lookup table, which most likely attributes to this game's uniquely lavish subsurface scattering skin. But this is just a fun little off-topic detail. A more relevant and important thing we need to analyze in Days Gone is how the pipeline projects non-moon/non-sun shadows, as it doesn't use shadow masks for these lights. We took the maximum amount of captures measuring all the possible scenario cost. All of these are full screen lighting draws. The middle capture data is the most important. Now let's extensively measure Unreal Engine 5's shadow mask creation on the same hardware and resolution. For many of these tests, shadow softening will be turned off to measure the simplest projection cost, and for the first test we're going to reduce the shadow map resolution by 4 times the amount in the Days Gone scenario, because the shadow map in the Days Gone test is actually a small atlas, and the light's shadow we measured is 1024 squared. Other than shadow map resolution and shadow sampling quality, the rest of the inputs are to be assumed, although the right-hand numbers show the same projection cost with the bit sizes reduced using hardware debugging tools. There is already 2 different major conclusions from this one test. Unreal's simplest projection, which looks thousands of times worse to the point of complete unusability, is already more expensive than the Days Gone method. The rendering experiment timing shows that the wasteful bits aren't affecting 3060 level hardware, so we're bound by something else. So let's do a variation test to confirm that we're bound by the simple action of pixel shaders, which, spoiler alert, we are. Then all of a sudden in the next variation test, input bit sizes seem to have an impact on performance. This is explained by the next main test. Even though we are reducing the input bit sizes, the draw is bound by the mere GPU work of accessing and writing to the 32-bit shadow mask. The similar timing suggests that we are pixel invocation bound, meaning it could be processing more arithmetics for free. The next 2 tests show how basic shadow softening affects performance, more than increasing the shadow map input size, as shadow softening requires multiple samples from the same inputs. Though this does mean we can increase the shadow map size by a good amount without a major cost because we're not bound by the size of our input bits. What Days Gone is doing is loading the draw with more input bits and logic so that the pixel shader invocations are better utilized. For proper context, this is a simplified way of looking at optimized hardware utilization, but there is a lot more we plan to cover in the future. Before you click out of the video, note that it requires a massive amount of labor to compile complex data and comparisons like this, and we do so with unique critical thinking and use the same exact reasonable consumer level hardware in every video, and it wouldn't be possible without our current Patreon members. As much as it may annoy you to hear it, we need to see revenue growth from these laborious efforts, and community support through Patreon is the best way to keep our work sustainable and spread the required culture that will support real progression. Consider helping us out by filling out this list with your name by the time we release our next video. Watch our channel content in order of release to understand the dire graphics industry optimization crisis and what solutions can lead to vastly better looking and better performing games. Until the next video.